Section 2.2 is derivative of a function at a point. We'll talk about what derivative means in just a minute. Alright, so the difference quotient, or what we're used to as calling the slope formula, or our average rate of change that we talked about in the last section, is f of a plus h minus f of a over h, and that's just delta y over delta x. It's the slope of the secant line in the curve from point A to a plus h. Okay, so we're going to use that again to find our average rates of change. So let's do a problem together to get started on this section. Find the average rate of change of f of x equals x squared over the interval 1 to 3. So let's do that first. So our plain old interval from x equals 1 to 3 is going to be from the point 1 comma 1 to the point 3 comma 9, and I found my y values by plugging 1 into my function and plugging 3 into my function. So using our formula, f of a plus h minus f of a over h, h is the interval, or the difference between my x values. In this case, if my graph looks like this, 2 goes up to 4, 3 goes up to 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is my curve of y equals x squared. So I'm going from the point A to the point a plus h. So f of a plus h is my f of 3 minus f of 1 over my interval, which is 2. I can also get that from saying 3 minus 1, just like it would in the old slopes. So that's 9 minus 1 over 2, which is 4. Now, this 4 is the average rate of change from 1, 1 to 1, 3. So find an equation of the secant line on this interval. So that's the line I want the equation of, this dotted line that I just drew. So it has a slope of 4, and it has 2 points, 1, 1, and 3, 9. So I'm going to use a slope of 4 to find my equation, and I'm going to use the point 1, 1. It seems easier. Using point slope form, that's my equation. I can also rewrite it in y equals mx plus b if I want to. I will get 4x. If I distribute this, I get minus 4. Adding my 1 is minus 3. Then I want to plot a graph of f of x and the secant line. I've already plotted f of x, so let's plot the secant line in a different color. Negative 3, and then 1, 2, 3, 4, up 4 to the right 1, 1, 2, 3, 4 to the right 1, and, well, goodness, and 1, 2, 3, 4 to the right 1. So there it is. It goes to the 2 points I had before and through my y-intercept down below. So that's using an average rate of change to find a slope. Average rate of change is slope of the secant line, and then one of the points on the graph to write the equation of my secant line. Alright, so instantaneous rate of change. Now what we're looking at is we are going to take that concept, and I'm going to draw just a little bit different picture, and I'm going to say if I am finding the slope of a secant line from a to a plus h, that gives me an average rate of change over the interval. If I want to find the instantaneous rate of change at a single point, that means what is the slope of one point? Now I can't do that using a regular slope equation, but if I make this point A and my point A plus h get closer and closer, in other words, if I bring this second point in, if I can get really, really close, where a plus h is almost on top of a, I'm getting really close to finding an instantaneous rate of change. So let's look at a new formula where we say that the instantaneous rate of change is the limit as h approaches 0 of the formula that we have been using, our difference quotient. The limit as h approaches 0 means that the point a plus h and the point A are getting really, really close to each other, and the interval, or the distance that I'm moving along the x-axis, my h distance, is really, really tiny. This is the derivative of a function. So the derivative, called f prime of a, this symbol is read f prime of a. Prime means the derivative. The derivative of f of x, which is my original function, is the limit as h approaches 0 of f of a plus h minus f of a over h. Super important. The derivative gives us the slope of a tangent line at one point. We have just figured out, using limits, how to find the slope at a point. So let's do it first using a calculator. Get a calculator out, and we're going to still use our good old f of x equals x squared function. So put that in under y sub 1 equals x squared. I want to find the rate of change at 0 or at x equals 1. So using an h of 0.1 in my calculator on your table, we want to first of all find what is the value of 1.1. In other words, my rate of change here is going to be f of a, that's my 1, plus h minus f of a over h. So if you plug 1.1 into your calculator, you'll get 1.21. That's my x squared, 1.1 squared. So it'll be, I didn't give myself enough room, 1.21 minus 1 over 0.1, which is 2.1. If I do f of 1.01, I'm using a smaller h minus f of 1 over 0.01. That's going to be 1.0201 from your table of values in your calculator, minus 1 over 0.1, and that's going to be 2.01. I'm going to make h even smaller. I'm bringing my second value really close to my f of 1, f of 1.001 minus f of 1 over 0.001 gives me 1.002001, which is, oh, I'm sorry, my denominator has to change also, 001 here, which is 2.001. And the last one, f of 1 plus h, a plus h, 0001, minus f of a over my h value is 1.00020001 over 0.0001, and that's 2.0001. You can see that as I'm bringing my two values closer to each other, as I am bringing on my graph, I started with a is 1, and I started with f of a plus h being 1.1, and I brought it closer to 1.01, and I brought it closer until I finally got something that was really close to 2. So from my table, it looks like, as I take the limit as h approaches 0, as I make h really small, of f of a plus h minus, and I'm going to put my 1 in there, 1 plus h over f of 1 over h, looks like it is approximately or getting closer and closer to 2. So my limit is approaching 2. Let's look at this algebraically. So again, I'm still going to use my f of x equals x squared, and I want to find my limit at x equals 1. So my formula says the limit as h approaches 0 of f of a plus h, in my case 1 plus h, minus f of a, or minus f of 1 over h. So algebraically, f of 1 plus h, let me rewrite my equation. F of 1 plus h is 1 plus h squared. F of 1 is 1 squared. Let's keep going algebraically. The limit as h approaches 0. 1 plus h squared is 1 plus 2h plus h squared. All of that minus 1 over h. Alright, 1 minus 1 will cancel. I'm going to get the limit as h approaches 0 of 2h plus h squared over h. Now, I'm still having a problem here. Remember we talked about finding a slope at one point. We would get 0 over 0. If I plug in h here, I still have 0 over 0. So let's keep working a little bit and look at the limit. Oops, excuse me. Don't want that. The limit as h approaches 0. I'm going to factor out an h on top, and then I can cancel those. Now, the limit as h approaches 0 of 2 plus h, well, if h becomes 0, this is just 2, which is what I found with my table. Now with my table, from the previous screen, this was still an approximation. It was approximately 2. I can never get, using just this formula, a point on top of itself. I have to have two distinct points. But when I go to my limit, you see what happens, and I can calculate it exactly. So now I know that the derivative, if I start with f of x equals x squared, I know that the derivative, f prime of x, at x equals 1, in other words, f prime of 1, is 2. So I can find my derivative, or my slope of the tangent line. That's what this means, the slope of the tangent line. I can find that at a given point using algebra. So, to write a tangent line, an equation of a tangent line can be found using the point a, f of a. That's the point that I want to find. And this font would not give me lowercase, so this is really a better way to write it. And using f prime of a for the slope. So let's go back to what we had. We had our f of x equals x squared, and I want to write a tangent line at x equals 1. So I need a point on the line. So I'm going to say f of 1 equals 1, which is the point 1, 1. And I need a slope. And that's f prime of 1, which I found to be 2. So my slope equals 2. So here's our function and derivative notation, and here's our good old Algebra 1, a point and a slope. So using my formula, y minus 1 equals 2 times x minus 1, and adding my 1, 2x minus 1. Okay, so if I were to draw my graph, I should have put a piece of graph paper on this slide as well. There's my y equals x squared. At the point 1, at the point 1, 1, I should have a line with a slope of 2 that passes through negative 1. This is my tangent line. So this is the equation 2x minus 1. This is my f of x, and this is my tangent at 1, 1. Okay, we will be doing some more of this together, and that's it.